Hi, my name is Richard Hobbs. I'm a postdoc in the Research Laboratory of Electronics here at MIT, where recently I've been working on the fabrication and testing of ultrafast surface plasmon-enhanced gold nanorod array photocathodes within Professor Karl Berggren's research group. Now, ultrafast sources of electrons are of interest for a variety of applications, including ultrafast electron microscopy and diffraction, where they may be used to study phenomena and materials on a sub-picosecond timescale. For example, at the Gedik lab here at MIT, they have used sub-picosecond electron pulses to study laser-induced restructuring of crystal surfaces by ultrafast electron diffraction, as shown in the schematic here. Now, ultrafast electron sources may also be used to feed free electron lasers. These are sources of coherent light, producing light anywhere from the microwave range all the way through to hard X-rays. And these ultrafast pulses of coherent light are produced from ultrafast electron pulses. For example, recently the Chapman and co-workers have used ultrafast pulses of electrons to produce 10 femtosecond pulses of hard X-rays to study the crystal structure of proteins by X-ray crystallography, as shown in the schematic on this slide. They use a 10 femtosecond X-ray pulse, which is shorter than the duration or the time scale of damage formation in the protein, and thus they can infer the structure of the protein before the protein is damaged by the X-ray itself. Recently, nanostructuring of photocathode materials has become of interest as a means to improve the efficiency of charge extraction from those cathodes, and also as a means to control the charge density distribution on the cathode surface. For example, Dombey and co-workers in this nanoletters paper have investigated electron emission and acceleration from plasmonic nanoparticles excited by ultrafast pulses of 800 nanometer wavelength light. They measure the energy spectra of the electrons produced using a time-of-flight spectrometer, and they found that the energy spectra could be modeled accurately based on a model of emission relying on a tunneling mechanism of electron emission. Similarly, Polyakov and co-workers have investigated electron emission from a plasmonic gold grating prepared by high-resolution electron beam lithography. Again, here using an ultrafast 800 nanometer wavelength laser to trigger electron emission. They found that the emission scaled with the fourth power of incident laser intensity, as shown on the plot here. Now, this fourth power scaling is indicative of 4-photon absorption in the photocathode material. They predict that if this scaling continues to higher laser intensities, their cathode, which is triggered by 800 nanometer wavelength light, may in fact outperform an equivalent UV-triggered photocathode consisting of a planar gold film at higher laser intensities. So in this work, we intend to investigate electron emission from plasmonic gold nanorod arrays in this higher laser intensity regime, and also to study factors affecting charge yield from such photocathodes, such as the applied static field, laser intensity, and the substrate gold interface in these cathodes. We begin by fabricating the gold nanorod arrays by high-resolution electron beam lithography, starting with an ITO-coated sapphire substrate. We spin coat this with PMMA to a thickness of 70 to 100 nanometers before patterning with 125 keV electrons from an Elionics F125 e-beam lithography system. We then develop the exposed PMMA, evaporate metal to our desired thickness by e-beam induced evaporation, and then lift off the overlying metal and PMMA in warm N-methyl peroleodone before gently ashing the surface to remove any residual polymer or organics. This allows us to produce arrays of gold nanorods, as shown here, prepared with a 3 nanometer titanium adhesion layer. This is to improve the adhesion between gold, which doesn't form a stable oxide, to the oxide substrate underneath. We test emission from these plasmonic gold nanorods using the setup shown schematically here. Our laser source is a titanium sapphire laser, which is pulsed with a central wavelength of 800 nanometers. It operates at a repetition rate of 3 kilohertz and produces linearly polarized pulses, which are 35 femtoseconds in duration. In our setup, we align the polarization, E here, the optical field, to the long axis of the gold nanorods to excite the surface plasmon resonance. The cathode resides in a high vacuum chamber held at 10 to the minus 8 millibar and is mounted on an XYZ stage on which we place an anode separated from the cathode by a 60 micron thick mica spacer. This allows us to apply an anode bias of up to 1 kilovolt and thus achieve a static field at the cathode surface of the order of 10 megavolts per meter. We measure the emission current both leaving the cathode surface and arriving at the anode, and we find that they match quite well in the majority of cases. So a typical emission curve looks like this. This is a log-log plot of emission current versus pulse energy. And we see that the emission current scales with the third power of incident pulse energy. Now, this third power scaling is indicative of 3-photon absorption in the plasmonic emitters. And for the bandwidth of the laser we use, 3 photons is equivalent to 4.5 to 4.8 eV of energy. Now, gold has a work function which has been reported to be anywhere from 4.7 to 5.3 eV, depending on the surface condition. So we can imagine that the emission occurs, as shown schematically here. Electrons near the Fermi surface of gold absorb 1 to 3 photons and escape over the vacuum level, or the vacuum barrier, and are collected at the anode in our setup. Now, recently, metallic adhesion-promoting layers, such as titanium used in our initial experiments, have been found to induce surface plasmon damping in gold nanorods prepared by e-beam lithography. In this work, published in ACS Nano, they studied by optical spectroscopy the surface plasmon damping induced by metallic adhesion-promoting layers. They found that the scattering intensity of gold rods prepared without titanium was significantly stronger than gold rods prepared without titanium, which is indicative of strong surface plasmon damping in the rods prepared with a titanium adhesion layer. So we decided to simulate this effect in our own lab. So we performed simulations using COMSOL multiphysics, using the finite element method. This allowed us to simulate the optical near field at gold rods prepared without titanium, shown on the top, and gold rods prepared with a titanium adhesion layer, as shown on the bottom here. We can see that the near field is significantly more greatly enhanced in the case of gold rods prepared without titanium, as shown. And in fact, if we look at a spectrum of the field enhancement and look at our wavelength of interest, here 800 nanometers, we see that gold rods enhance the optical field by a factor of 2 more than gold rods prepared without titanium. So we decided to go ahead and try and fabricate these gold rods without a metallic adhesion-promoting layer, and here's what we produced. We've shown that we can produce gold rods in the absence of such adhesion-promoting layers, although we do see an increase in the number of interstitial particles, as you can see here, which is most likely due to delamination of gold from the rods during the liftoff process. However, the rods still compare quite well morphologically with those prepared with a titanium adhesion layer. So we went ahead and measured emission from those rods. And what we found is that gold rods prepared without a metallic adhesion-promoting layer, shown in black here on this curve, showed significantly stronger emission than gold rods prepared with a metallic adhesion-promoting layer, titanium here. And if we look at the lower end of the pulse energy scale here, we see that the gold rods, in fact, have a 26-fold increase in emission current with respect to those prepared with a titanium adhesion layer, for a region where both display 3-photon scaling. So how do we get some information from this? Well, if the emission current for gold rods prepared without titanium is 26 times larger than for gold rods prepared with titanium. And we know that the emission current is proportional to the third power of pulse energy, which is equivalently to the sixth power of the optical field. Then we know that the optical field at the surface of a gold rod must be 1.7 times larger than the optical field at the surface of a gold rod prepared with a titanium adhesion layer. And this factor of 1.7 is in good agreement with our simulation from the previous slide, which shows a factor of 2. So when we return to our emission current scaling curves here, we see that whilst the emission scales with this third power scaling at lower pulse energies, it's suppressed at higher pulse energies and bends away from this third power curve, or this line here. One possibility for this suppressed emission current is the onset of space charge limited current. We can envisage this pictorially here using this simple schematic. It's a diode configuration, so a cathode and an anode separated by a vacuum gap. And we apply a bias across the gap, resulting in a static field, E DC, shown here. Now, if we introduce an optical pulse propagating into the surface of the cathode, this pulse will result in the production of a sheet of charge at the cathode surface, which will grow in size and density. So too will its associated space charge field, ESC in this case, until the point where the field due to this sheet of charge will eventually cancel the applied static field in this region between the sheet of charge and the cathode surface. This means that electrons subsequently emitted from the cathode will be repelled back into the cathode surface by this charge sheet, resulting in a suppression of emission current. Now, as we can see from this simple diagram, the space charge limited current should be strongly dependent on the applied static field or the applied anode bias. In fact, for an ultrafast optical pulse, the space charge limited current is linearly proportional to the applied static bias. So this stands to reason, so we should investigate how the emission current scales with the applied anode bias for our plasmonic gold nanorods. And here's what we've done. So we show a plot here, a linear plot of the emission current as a function of applied anode bias for several different pulse energies or laser pulse energies. And what we see on the left-hand side of this graph is that the emission current scales linearly with the applied anode bias, which is indicative of space charge limited current. However, once the applied anode bias is raised above approximately 450 or 500 volts, the emission current now becomes independent of the applied anode bias, especially here for lower pulse energies of 25 nanojoule and 37.5 nanojoule. So this indicates that the emission current at these higher biases for this lower pulse energy or lower laser intensity is space charge free. So if we return to our scaling of emission current as a function of applied laser intensity or applied pulse energy, and now look at the scaling of emission current as a function of pulse energy, but for this higher range of anode bias values, here's what we see. So the emission current scales with this multiphoton scaling, as we saw previously. So here, 3-photon scaling at lower pulse energies. However, at a pulse energy of 27 nanojoule, here, this dashed line, the emission current deviates from this multiphoton scaling irrespective of the applied anode bias applied. So it deviates at the same value of pulse energy irrespective of the applied anode bias, which suggests that this deviation is not, in fact, induced by space charge limited current. It must be a fundamental change in the mechanism of emission. Now, recently, a model for this deviation has been proposed based on studies of strong field ionization of gas atoms. And what this model suggests is that at low laser intensities, the emission rate scales with, according to a multiphoton absorption mechanism on the left here. This is lower laser intensity. But at higher laser intensities, the emission current is better described by a tunneling mechanism. And that this transition between these two mechanisms occurs at a Keldysh parameter gamma of equal to 1 or 2. So what is this Keldysh parameter? Well, the Keldysh parameter basically relates the work function of the material, phi here, and the ponderomotive potential, where the ponderomotive potential is effectively the wiggling energy of an electron in a strong oscillating field. And this ponderomotive potential is directly related to the intensity of the applied, of the laser. What this says is that at low values of gamma, the mechanism of emission should be tunneling or field emission. And at large values of gamma, the mechanism of emission is multiphoton emission or photoemission. So what this begs the question, what occurs at this intermediate range where gamma is of the order of 1? And this is what we show schematically here. So as we just said, at large values of gamma, we're in this multiphoton emission regime where electrons are absorbing 3 photons and escaping over the vacuum barrier. However, at gamma close to 1, the energy states in the vacuum have been deformed or modulated by the ponderomotive potential. What this means is that the energy level or the effective work function is now raised by the ponderomotive potential of the laser during the duration of the laser pulse. When the pulse has left, these energy states return to equilibrium, and now the electron can't escape through this barrier, and this channel is closed. This multiphoton emission channel has been closed, and electron emission proceeds via a different mechanism, this tunneling mechanism. So here's what we see on our emission curve. So at low pulse energies, electron emission is via this multiphoton regime or a multiphoton type emission. And this transitions to a tunneling type emission at a value of gamma equals 1.5 for our system, which is in good agreement with the reported values of 1 to 2 from the literature. So if we return to this original plot from Polyakov and co-workers and we compare the performance of our plasmonic photocathode to their work, what we see is that for a 200 nanometer pitch array of gold nanorods, excited again here using a femtosecond 800 nanometer wavelength laser, we see that the emission is comparable to that from a UV-triggered planar gold cathode. So what we're seeing here is that emission with a much lower energy photon in this 800 nanometer wavelength laser is comparable to a much higher energy photon from a UV laser because of this plasmonic enhancement in these gold nanorods. So to conclude, we've seen enhanced emission from titanium-free gold nanorod arrays. We've determined the contributions of space charge and tunneling emission to the emission current or the charge yield from our photocathode. And we've observed a charge yield for high-density arrays of gold nanorods, which is comparable to UV photoemission from planar gold, despite the fact that we're using an 800 nanometer wavelength laser here. We propose that the charge yields from these photocathodes could be increased even further still with these 200 nanometer pitch arrays by increasing the applied static field, so perhaps in placing this photocathode in an RF injector to achieve much stronger static fields. In our experiment, we use 10 megavolts per meter. In conventional RF guns, we can achieve static fields of the order of 100 megavolts per meter. So it just remains for me to thank Raphael and Jeremy, who helped out with ITO deposition, Jim Daly and Mark Mondel from the Nanostructures Laboratory, who helped out a lot with fabrication, and Joel Yang from Singapore, whom with I had a lot of useful discussions, and the Gordon and Betty Moore Foundation and DARPA for funding this research.